This is example 3 in Module 12. It's exactly like example 2 in terms of the lenses that are used and their configuration. The difference is where the object is placed, and we're going to see that that actually makes a significant difference. So, the approach is the same. We just treat, we start off by taking the object and looking at the effect of lens 1 and just completely ignore lens 2. Then, once we get that image, we treat it as the object for lens 2, and we completely ignore lens 1. Alright, so for lens 1, oops, I always put an E on the end of lens. For lens 1, we've got 1 over object distance plus 1 over image distance is equal to 1 over the focal length. The focal length is the same as it was before, so that's plus 24 centimeters. But the object distance is larger. Now it is plus 30 centimeters. All right, if I draw the ray diagram for this, this ray that comes in parallel to the optical axis is going to be bent towards the focus. The ray that is going through the center won't bend at all. Oh, wow, look at that. Which means that we get an arrow drawn right here. So, this time the image formed by the first lens is behind it. So we expect a positive image distance. The tricky part here is what we do with that for the second lens. So, we'll have to talk about that when we do the second lens, but this image is also behind the second lens. So how do we account for that? Well, let's worry about the first lens. Alright, so the image distance is 1 over f minus 1 over d O inverse. And I get, it's like 119.99. I'm just going to round that to 120 centimeters. So the image is formed 100, and this time it's positive. The image is formed 120 centimeters behind the first lens. Now we go to lens 2. So how do we handle an object that is behind the lens? So a real physical object, right? We would never encounter this. Right? If I had an object that was behind the lens, then I would say, well, actually, I'm just looking at the ray diagram backwards. I should have drawn, look from the other side, and the arrow would be on the left. But in this case, we don't have a real physical object. We have an object that is due to another lens creating an image. And so what's really going to happen, if we physically look at what's going to happen to the rays through this system, when these rays that I have drawn here go through this second lens, they're going to be bent more, right? And the effect is that they're going to change the position of the image that is formed. And we really can't draw, I can't draw a ray diagram from this image here that goes backwards, right? It's not like the rays, I guess if I tried to draw it, it would go like this, right? This one comes in parallel, this goes like this. It's not that the rays go through the first lens, go to that image, then turn around and go back through the second lens. No, the rays are only going from left to right. But it turns out that we can actually account for where this image, final image, will be formed by just treating this image that we have here as an object. The object is behind the lens, which means that it should have a negative object distance. Alright, so that means if I write down the focal length is still 9 centimeters, and that's plus. I write down the object distance. The object distance is how far the image from the first lens is from the second lens. They're 10 centimeters apart. The image was 120 centimeters behind the front lens, which means that this is going to be 110 centimeters. Since the object for the second lens is behind it, we're going to call that negative. That means it's a negative object distance. So this should be negative 110 centimeters. Formula for DI is the same. And I get a plus 8.319 centimeters. And that's a positive image distance. And when I have a positive image distance, it means that the image was formed on the side of the lens that light is going to. So just because the object distance was negative, right, the object is on the back side of the lens, it doesn't change the sign convention for the image distance. Since that image distance is plus 8.3, that means that the image is going to be formed somewhere around here. Let's see here. This is 9, so it's probably going to be formed somewhere around here. Whether or not that image is going to be upside down or not, I guess I can, it's hard to tell just by looking at the ray diagram, so I'll just calculate the magnification to determine whether or not that image is going to be upside down or not. The second question is whether or not this image is real, and to determine if the image is real, it's the same as it was before. Are the light rays going through that image? So again, this is sort of what's actually happening to the light rays. Right? We don't really, it would be hard for us to draw a ray diagram that showed how these rays bend, because this ray that gets incident on that lens is not parallel, so it doesn't have to go through the focal point. This ray is not going through the center of the lens, so it's probably going to bend a little bit. But determining how it bends would be difficult to do in a ray diagram, but we just calculated where the position of that image is going to be, so we know where the image is going to be formed. So if I put a sheet of paper here, the light rays are actually going to strike that sheet of paper, which means that this is a real image. And then the last part is to calculate what the total magnification is. And we have to do that the same as we did before. We calculate the magnification for each part. So we get a magnification of -4 from the front lens, which means that it's upside down and it's 4 times bigger than the object. And the magnification for the second lens centimeters is a, let's see here. Oh, I need to be careful here. So this negative sign is from this, but the object distance is negative. So this is going to be plus 0.0756. So that means that the second lens does not invert the image again. The total magnification then is -4 times 0.756, which is -0.3025. So that means that the final image is inverted and it is smaller than the object. So if we come into a scenario, I mean, this is exactly the same setup as the previous problem, the previous example. The only difference is that we've moved the object. So before we had an object here, now we have an object here, and that changes things significantly. So when we have a scenario where we get an object that is behind the lens or the mirror that we're trying to analyze, we just have to treat that object distance as negative.